Good morning, Elliot.
Good morning.
How are you doing?
Fine.
Good. Neo, how are you?
Doing good.
Good.
Yep.
All right, how's everyone doing this morning? Hopefully okay. Tomorrow is the math tutoring day or whatever. Wait, am I frozen? Okay. Tomorrow is the math tutoring day, which means we don't really have a lesson or anything. So all that happens is I'll take attendance, and then if you guys have questions, you can ask questions, and if you don't, you can go after that. So that's basically all that's happening tomorrow. You guys have a problem set due Friday. So if you do have questions for your problem set, that would be a good day to do that. But you can ask questions on whatever you want. So if you have questions, you can ask them. If you want to just hear other people's questions, you're fine with doing that as well. If nobody has questions, you guys just check in and you go. But it's more a day for you guys, like if you need to work on your problem set, if you want to go back to bed for 40 minutes or whatever, that you guys can do that stuff. So that's kind of what's going to happen tomorrow. I am still supposed to take attendance, so I need you to check in at some point, but you don't have to stay. That's basically it. So we're gonna do notes, and then Friday we don't have any notes either. So I'm aiming for like 3 sets of notes a week. So it's not just sitting and being lectured for in the entire period. So on Friday we're gonna do a group thing. So I'm gonna do breakout groups and see how that works, and give you guys a group thing that'll be a bonus on your test, which is still not for a while, but it'll be over the first couple sections of notes. And kind of more challenging problems than you're seeing on your homework, and probably more challenging than you'll see on your test. Just kind of a chance to think a little more in depth about problems. And oops, hold on, I'm gonna change my Wi-Fi real quick. Hopefully it doesn't destroy everything. So I think I've got a better one that hopefully will work better. Everyone seems real choppy. Okay. Can you guys hear me? Okay. Maybe it's someone else's Wi-Fi that's making it look choppy, but some of you guys are not moving, and so it makes me wonder if something's going on with my Wi-Fi. Okay. So we are going to keep going. Your problem set tomorrow is only through 11.3, meaning you guys have done all the stuff you need to do for, we've done all the notes for that already. The 11.4 and 5 are on next Friday's homework. So far what we're doing, you guys have quite a bit of time to kind of figure that out if it's making no sense to you. So what we're looking at today is lines and planes in space. So these are kind of like basic equations. So think like algebra 1, when you're first doing 2-dimensional graphing and things like that. you learn how to graph a line and things. That's kind of where we are in 3D, is how we kind of graph and visualize things like points or lines and planes. So first, just like in 2D, we need some basic information in order to do that. So if you think back to when you have to determine the equation of a line, the main information that you want is you need at least 1 point on the line. All right, and this is again back in 2D. This is kind of review from, I don't even know when you guys took Algebra 1, long time ago. So we have a point, and then we want a slope. You can obviously use a second point to find that slope, but we want a slope which in math we define as the change in y over the change in x. It's kind of arbitrary that somebody just decided that's how we kind of describe the direction that a line is going, by doing change in y over change in x. And then we can kind of plug that information in to an equation for a line, and we can get an equation for a line, which is basically just describing a relationship. So we also have relationships in 3 dimensions. We can do lines, we can do planes, we can do all sorts of things, just like in 2D, you can have parabolas and cubic functions, all that stuff. But this is just describing a relationship that I can plug an x in and it'll output a y, and I can get a bunch of points that have a specific relationship with them. Okay, in space, we'll use a point in the same way. We need a point on the line. But slope doesn't really make sense in space, because in general, slope is a ratio of 2 values, because we have 2 main kind of directions in 2D. We have an x and a y direction, and so we can do a ratio of those 2 values in 2D, but in 3D we have 3 directions, x, y, and z. And so there's no convenient way to come up with one ratio that compares all 3 values, because ratios usually compare 2 values. So we don't really use kind of rise over run or whatever. Instead, we use a directional vector to show the direction of the line. So you basically pick any vector you want parallel to the line. And the idea is the vectors will be scalar multiples of each other, and slope, you could do like a slope of 1/2 is the same as the slope of 2/4, and the same as the slope of -3/6, or sorry, -3/6, -3 over -6. We could take multiples of that slope and get the same slope, right? Well, directional vectors are the same way. We could take multiples of the directional vector and it's not going to change the equation of the line. But it's basically just telling you how to move in the 3 directions. So we'll use a directional vector like 1, 3, -7 would say I could start at a point and I could move 1 in the x direction, 3 in the y direction, and -7 in the z direction. 1, 2, 3, 4, 5, 7. And that there could be another point there, and that would be another point on the line. Kind of like with slope, we know we could move up 1 over 2, up 1 over 2, up 1 over 2, and get to other points. The directional vector is the same idea. It's giving us 3 values that just say in the x, y, and z direction, I can move there, and I will be at another point on that line. So we'll use a directional vector similar to how we would use the slope. Oops, my iPad doesn't want to move. There we go. So we'll have some vector. I'm going to call it vector v with components A, B, and C. Those are called directional numbers, and they represent how far you would go in the X, Y, and Z direction to get to another point. Not the next point, because there's infinitely many points, but just to another point on the line. Okay, so we've got directional vector that's filled with directional numbers. And that's what we'll use to come up with our line. So instead of a point and a slope, we want a point and a vector running parallel to the line. So if we have our line, we can use any vector that's like parallel to the line. It doesn't really matter. We just pick one that's parallel. Okay, so we also can't express it as a single equation. So like in 2 dimensions, we obviously can do be like y equals 2x plus 3, and that's a line. If we do y equals 2x plus 3 in 3 dimensions, that's actually going to be a plane. A plane is our kind of first order equation. If you think of everything to the first power, that'll give you a plane, not a line. So the only way to express things like lines and curves is with parametric equations. If we do just one normal equation, you'll get a solid, like a sphere or a plane or a cone or whatever. If you do parametric equations, you can do things like curves and lines. So what we'll use is parametric equations, and it'll basically look like 3 linear equations. We'll have x equals, we'll use our point, x1, plus our directional number a times t. Okay, and that'll basically say we'll start at this x value, and then we'll move a multiple of a in the x direction. And then y will do the same thing, y1 plus bt, and z will be z1 plus ct. Okay, and these are our parametric equations. So I could take like t equals 1, plug that in, and what would come out is a point. I could plug in t equals 2, plug that in. What would come out is another point on the line. T equals 3, plug that in, and I would get another point on the line. Okay, so you'll get 3 little equations that will generate the points on your line and describe the points on your line. So we'll use parametrics, and that'll be true with any curves that we want, anything that's not a solid object like a sphere or something. If we want just a curve going through space, we need to use parametric equations. All right, so working backwards, we could look and we could kind of define some stuff about our line. So if we have these 3 parametric equations, x equals 3, y equals -4 minus 3t, and z equals 2t, we could go backwards and kind of generate, we could generate any point we want, but we could find our directional vector. That's just the coefficients of t. So notice the x parametric equation has no t's. That's telling me that the directional vector there was 0. And then the coefficient of t in the y equation is -3. And then the coefficient of t in the z equation is 2. So we know our directional vector. So if we graph that vector, it would be parallel to the line. And then we could get a point that's on the line. The easiest one is basically make t equal to 0. So set t equal to 0, and we have 3, -4, 0. But we could get other points too, right? You could do let p equal, well, I'm going to do that p naught. You could let t equal 1, or you could let t equal 2. And we could just generate as many points as we want. What we should see is all those points would fall in a line. You could plug in fractions, decimals, obviously, all the same stuff you guys would do in Algebra 1 or stuff before this class. But you could just start plugging in t's and you could generate as many points as you want. Okay, there's other forms that a linear equation can take. So I'd say the most common is the parametric equations, but there's also something called symmetric. So think in algebra, we can do point slope form, or we could do slope intercept form, or we could do the standard form of a line. Well, same idea here. There's other forms that you could do. And basically what we do to get the symmetric equations is we solve these equations for t. So like here, if I solve for t is going to be x minus x1 over a, right? If I subtract x1 and then divide by a, here t will be y minus y1 over b. And here t will be z minus z1 over c. And so our symmetric equations are saying at every at every point we're having the same t values. So we're just setting those things all equal to each other. since we've solved for t, which all of them have in them, I'm just setting them all equal to t, then subbing in the other ones where the t's are. So these are called the symmetric equations. I would say this is not as convenient for graphing. Most of the time, your different forms of an equation have specific purposes. So like I would say slope intercept form of a line, easy to graph, right? We're really used to the b being the y-intercept and then having the slope and graphing that way. It's not very convenient to find other points on the line where like point slope form might be using other points than the y-intercept. So here, I would say the parametric form is the easiest to graph points that are on the line. Just plug in a t, get a point, plug in a t, get a point, plug in a t, get a point. Symmetric is the easiest one to me to figure out if a point is on the line. We could plug in an x, y, z and see if we get these three equal equations or three equal things here. So to me, that's what symmetric is most useful for, is if I give you a point and say, is this on the line? You could plug it into the symmetric equations and pretty quickly see that. So it's not a big deal, but basically this for lines, we want a directional vector. This is parallel to the line. We want a point on the line. Okay, any point on the line is fine. Oops, my thing didn't change. Hold on. Let me reshare because it didn't seem to want to change there. All right, so I have a little summary page that kind of gives you the main ideas of the lines. So you need a directional vector that's parallel. You want a point on the line, and then we can come up with our parametric equations. X equals x1 plus at, y equals y1 plus bt, z equals z1 plus ct. Or we could do our symmetric equations, x minus x1 over a equals y minus y1 over b equals z minus z1 over c. Okay, so those are the main points of a line, is you could write the equations parametrically, symmetrically. You could take points. Obviously, if we don't have a directional vector, if you have multiple points, you can find the vector in between. So it's not that you have to be given a vector. You should be able to be given a bunch of points and graph a line. Just like if you have points in 2D, you can find a slope. All right, so find parametric and symmetric equations for a line that passes through the points given here. So I'm going to label the points A and B. So again, just like in Algebra 1, I normally, every time we find the equation for a line, I say we need a point, we need a slope. Well, here we need a point, which we have. You can use either point. And we need a directional vector. So I'm going to find vector AB. You could do BA, doesn't matter. And remember, to find vector between 2 points, we just subtract the terminal minus the initial point. So I have 1 minus a negative 2 is 3. 3 minus 1 is 2. And 5 minus 0 is 5. So that vector should be running parallel. Technically, any multiple of that vector will also work. And then we need a point. You can use either point. It doesn't matter which. And then the parametric form then would be x equals negative 2 plus 3t, y equals 1 plus 2t, and z equals 0, which you don't have to write, plus 5t. And again, the coefficients of t could be different. They could be any multiple of 3, 2, 5. And then the point, you could have chosen the 1, 3, 5. And it would just mean you're going to start at a different point on the line. When I plug in t equals 0 and you plug in t equals 0, you might start at different points. But as we plug in a bunch of t's, we'll end up with the same line, the same kind of gathering of points there. Symmetric is just x minus 2 over 3 equals y minus 1 over 2 equals z minus 0 over 5. And so to me, this is a more concrete example. I could plug in t equals 1, 2, 3, 4, 5 to the parametrics and generate a bunch of points. Symmetric is good for saying is 1, 2, 3 on the line. Well, you could plug in x equals 1 and we'd have 1 minus 2 over 3, 2 minus 1 over 2, and 3 over 5. This is not true, so no. Okay, you could literally plug those in. If I get 3 equal numbers, yes, it's on the line. If I don't, it's not on the line. So that's what symmetric is most useful for me, is plug in a point. Up here, you'd have to plug in the point, solve for the t, and figure out if you're getting the same t's, so it's not super convenient. Okay, for a plane, this is on the test, this is one of the most missed problems, is an equation for a plane. And it's, I don't know why that is, because it's not really any more complicated. It's just that people don't really seem to like grasp what we're using here. So what we use to come up with the equation for a plane is if we have a vector parallel to the plane, and we have a vector perpendicular to the plane, when we take the dot product, it'll be 0, right? We're going to call the vector perpendicular to the plane n. Okay, for normal is why we choose n. For a vector parallel to the plane, what we're going to do is we're going to take xyz is any point on the plane. Okay, just like x and y in the line y equals 2x, the x and the y represent points on the line. Well, here we're going to say xyz represents any point in the plane. x1, y1, z1 is a specific point on the plane. Okay, so similar to y equals 2x plus 4. The 4 represents a specific point on the line y equals 2x plus 4, where the y and the x represent all the other points. Okay, and so we're going to use that to find a vector parallel to the plane by just, again, using subtraction. Right, x minus x1, y minus y1, z minus z1 is a vector parallel to the plane. I just took any point on the plane and the specific point on the plane and subtracted, and I got the point in between. Okay, so if we look at our plane, we're saying I have some point x, y, z, and I have some point x1, y1, z1. And if I subtract terminal minus initial, so you're basically getting like this vector. N would be perpendicular, meaning n is going perpendicular, and the entire place that the equation for a plane comes from is that we know then n dotted with that vector, since one is parallel to the plane and the other is perpendicular, will give me 0. So let's say n was A, B, C, or whatever it is. When I take the dot product, I get A times x minus x1 plus B times y minus y1 plus C times z minus z1 should be 0. That's the equation for a plane. And the thing that a lot of people do wrong on the test is they try to find a vector parallel to the plane, just like we do with the line. They try to do kind of a directional vector parallel to the plane. Well, the problem is the derivation of this formula comes from that the dot product should be 0 because they're perpendicular. That's where the equals 0 in the equation comes from. So we need to find a perpendicular vector and take the dot product with that. So the ABC is perpendicular to the plane, not parallel like a line. But otherwise, it's really not super complicated otherwise to do to find that. So we want a vector orthogonal. Okay, this is where the formula comes from, is the fact that they are orthogonal, they will have a dot product of 0. So don't use parallel, okay, like we do with lines. That's the biggest thing. People do the lines just great. They go to the plane and they start using the same type of vectors. The whole way we come up with the equation for a plane is from the orthogonality and the dot product. Okay, so standard form is what we just showed. Oops. A times x minus x1 plus b times y minus y1 plus z, oops, sorry, c times z minus z1 equals 0. Don't forget the equals 0. That's another thing people forget. It's an equation for a plane equation implying there needs to be an equal sign. Okay, and this is where A, B, C is perpendicular to the plane. Okay, and then x1, y1, z1 is any point on the plane. And then x, y, and z are literally x, y, and z. You leave that alone. So it's just like the equation for a line or whatever. You want an x, a y, and a z in there. Okay, if we were to distribute and simplify, so distribute the ax minus, ax1, and then plus by minus by1, cz minus cz1 equals 0. And kind of gather all the constants. So ax plus by plus cz, those will all have literal variables x, y, and z in them. But the minus ax1, minus by1, and minus cz1, those are all constants. Okay, the x1, y1, z1 is a specific point that you've put in there that's on the plane. The a, the b, and the c are specific values from the vector. This is a constant or a scalar that we can call d. Okay, and then that leads to what's called the standard form, ax plus by plus cz plus d equals 0, or ax plus by plus cz. Sometimes they write equals d on that side instead. They subtract the d onto the other side and just call it d. They just gather all the constants together. So if you ever see, for example, if we were to graph 2x plus 3y minus 4z equals 10, that's a plane. Similar to the last one, standard form, it's really easy to see the point and the vector, the perpendicular vector. General form, you kind of lose the point. But general form is good for telling if a point's on a plane. Standard form is good for taking a point and coming up with the equation of a plane. But either one is fine. You probably see this one more in problems. And we use this one more when we come up with an equation of a plane. Okay, but if I see a bunch of x to the first, y to the first, z to the first, those are planes. If I start squaring x's and y's and z's, or multiplying x's and y's and z's, that's where we'll get other things. All right, so we have several things that we want to do. I'm not going to do the graph, for example, because I've got a picture right here. So we can find the angle between planes. So angle between planes, meaning this little acute angle here. If I have two planes crossing, what is the angle that they make with each other? We don't really need a new formula for that. We can just use their normal vectors, which is evident in the equation, right? When we see the equation for a plane, the coefficients of the x, y, and z, those are the normal vectors. And so we just find the angle between the normal vectors, because if I have the planes, the normal vectors are just shifted 90 degrees, but they'll have the same angle between them as the planes have. And so we use that u dot b over the magnitude of u times the magnitude of v equals cosine theta. And we just plug in the normal vectors. So we'll use the normal vector for one plane, the normal vector for the other plane, instead of u and v. We'll use the two normal vectors of the plane. And then vectors could have an obtuse angle between them. Planes, we're looking for the acute. Since they cross, there's always going to be one obtuse and one acute. And the way we do that is we take the absolute value. Remember, the negative numbers give us the obtuse and the positive give us the acute. We take the absolute value, and then we'll end up with just that acute angle between the planes. Because that's generally what we're referring to with angle between planes. Okay, so that's just a formula. Oh, I just saw someone asked a question earlier. Shouldn't be x plus 2 over 3. I may have made a typo on one of the other ones. Someone just pointed out, but it was a while ago and I didn't see the chat, sorry. So yeah, I'll go back and look in a second. But I want to not run out of time here. Okay, so find parametric equations of the line of intersection. So there's all sorts of ways that you could kind of algebraically look at how to deal with things. So say we have two planes and they meet. Planes generally meet in a line. They can't meet at a single point. So think if you were to cross two planes, they're going to meet all along a line. So what if we have these two planes and we only want the equation of the line that's their intersection? We'll do elimination, okay, substitution, elimination, just kind of algebra stuff. We'll try and eliminate one variable from the relationship, because otherwise it's really hard to come up with an equation. So I'm going to take this equation, this first one, I'm going to move it over here and I'm going to multiply by -2. So that I have -2x plus 4y minus 2z equals 0. Multiply the entire thing by -2. This is like what you did in Algebra 1 to solve systems of equations. And just remember, if I multiply the entire equation by something, it's the same plane. I haven't actually changed the plane. And that way I can add them together. And notice if I add them together, the x's will cancel and I end up with 7y minus 4z equals 0. And once I'm at any two variables, it doesn't matter which one you eliminate. Once I've got this relationship, 7y equals 4z, or y equals 4/7 z. Once I've got this relationship, the easiest way to come up with a parametric equation, set of parametric equations for the line that will meet these relationships, is I'm just going to set z equal to t. Notice that y is 4/7 z, which means y will be 4/7 t, since z is t. And then I use any of the equations I want to find the x. So x minus 2y, or 2 times 4/7, plus z, so plus t, should give me 0. So x minus 8/7, should be a t, sorry. 8/7 t plus t equals 0. So that t this is 7/7 t. So this is x minus 1/7 t equals 0. So x is 1/7 t. So I could use the equations x equals 1/7 t, y equals 4/7 t, or z equals t. And that's going to describe a line that's all along the plane. So I just solve a system of equations, and then I can literally just let any variable I want be t, and then use that relationship that I developed with systems of equations to find the other things. It's probably more common. Remember, we can take any multiple. So we might actually see, like if you were to look at a key for a homework problem like this, where they've simplified, meaning they've multiplied everything by 7. By 7. And that's going to describe the same line. It's probably considered more simplified to not have all those fractions and things, is to have cleared the fractions and have it be as reduced and simplified as possible. It doesn't matter to me as long as you realize any multiple of that is going to describe the same line. So technically you could have other things as well. You could have solved for z instead of for y and come up with something different. You could have eliminated a y or a z instead at the beginning and come up with something different, but it should end up being basically a multiple of the same line. Okay, sketching planes in space. We sketch what are called the traces. Okay, so generally we just kind of sketch a little piece. So like you might see a little triangular piece. That's not the whole plane, right? It's continuing on in all directions, the plane. But a lot of times we just kind of want to see where it's cutting through the axes. And so we just plot the traces. And so literally we find that like this point is where x and z are 0, and we just find the y. This point is where the y and the z are 0, and we find that point. This is where x and y are 0, and we just find the z. You plot those points and you kind of connect them. So it's common to see like a trace or be asked to kind of sketch the trace of a plane so that you can kind of just picture where the plane is going, okay, where it's kind of cutting through. So we sketch the trace rather than try and sketch the plane, because if you sketch a plane, it may or may not. Some of you guys, I've noticed when people turn stuff in, some people are very good at drawing in 3D and some people it's really difficult. I find it really difficult. So yeah. Okay, so here, if we wanted to sketch the trace, I would just find what happens when y and z are 0, x has to be 4. Okay, and then what happens when x and z are 0? Y would be 6. And then when x and y are both 0, z would be 3. And so this is the part of the plane over the first quadrant. And again, it would extend in every direction, just straight, flat in every direction. But that kind of gives us an idea of where it is in space, where that plane cuts through. Oops. When do we get out? 30? Is it at 30? Okay, so we're gonna, again, run out of time like usual. And then I'll just finish the rest of it at a later time. But we'll go ahead and get as far as we can. So if a variable's not there, it's still a plane. Okay, so like 2x plus z, it's still a plane. It's gonna be parallel to the axis of the variable that's missing. So like in this case, it's gonna run parallel to the y-axis. It's not gonna ever intersect the y-axis. So our trace won't have anything hitting the y-axis. It's kind of gonna run parallel to the y. So we could still find the x, right? If z is 0, x would be a half. And if x is 0, z would be 1. And so we have basically that trace. And then the plane is running parallel to the y. So it would be kind of going this way. Okay, meaning you won't end up with the other traces because it won't ever intersect the y-axis. So kind of picture it running parallel to the y-axis, but it is still a plane. Again, if you ever see x to the first, y to the first, z to the first being added together, not multiplied or things, that's a plane. So I'm going to end with the last sketched one, and then we'll do the last problems at another time. But if 2x equals 4, that's also a plane. Okay, and similar, it's going to be parallel to the plane of the missing variables. Meaning in this case, it'll be parallel to the YZ plane. It will not intersect the y-axis, the z-axis, or anything in the yz plane. Speaking of planes. Okay, so we'll only have an x-intercept, 2, 0, 0. And then it'll go parallel to the YZ plane. So it'll be going exactly like the YZ plane, but it'll hit the x-axis not at 0, but at 2. So it's like we shifted it forward. So anytime you see relationships between variables to the first power being added or subtracted, whether they're all there or not, those are different planes. So you want to get really used to realizing like that's a plane. That's like a linear equation in 3 dimensions is the plane. It's kind of a basic simple equation. Okay, so I'll finish the rest of it. Not tomorrow, because tomorrow is just a regular study day. Maybe Friday, but maybe I'll just do it Monday. This isn't relevant for your Friday homework, so it doesn't really matter. We can do it later. But yeah, that's it. So you guys have a good afternoon. And again, tomorrow, just check in. If you have questions, bring those questions and ask them. If not, just check in, say hi, and I'll take attendance. And then you guys can go back to resting, doing homework, doing whatever it is you need to get done. And then I'll see you guys on Friday as well.
Thank you.
Right.
Thanks,
Bye,
Mr.
guys.
Smith.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Bye.
Bye.
Mr. Smith, I have one question.
Okay.
So I was doing the first, like the 11-1 homework, and I noticed that 82 is not in the solution.
82 was that assigned, is you're saying, but it's not one of the solutions?
Uh-huh.
Any of the even numbers don't appear in the solutions. I can post the answer if you're wanting. Is that what you're basically wanting to see if you did it right?
Yeah, and like how you do it.
Okay. So I'll post that in Google Classroom today.
Okay, thank you.
So Neo, did I do one of the
Yeah, I think
I
it was.
subtracted instead of added or something?
Yeah, I think that was it. I think it was on the slide about like it was x plus 2.
Oh yeah, I see where I did it. Yeah. All right. Thanks for pointing that out. Whenever I finish the notes, I'll go back and share that with people. But yeah.
Okay, yeah. I was just making sure I didn't just like subtract wrong on my end.
Nope,
Because...
I did.
All right, thank you.
Yeah, thank you.